Truly excited to be back again. I actually talk to you more about, I would say, transition method chemistry and seeing how this is going to be building up to catalysis. We're going to dive now into reactions in transition metal complexes. On our previous video, we looked at the different bonds that are being formed. In here, we're going to see the reactions, and this particular video is going to be in parts, so it will be like a part series. And in here, we're going to look at first the oxidative addition. This is actually going to be focusing a little bit on how this is going to be inserting metal atoms into a single bond between two atoms, and this will lead to the metal in between the two atoms right there. So how is this going to be established in this term oxidative addition? In here, starting off with the oxidative addition, this is where ligands without a lone pair of filled pi type orbitals interact only by breaking this particular sigma bond right there, resulting in the oxidative influence on the particular metal by an increase in oxidation number happens on this particular metal as a result of this particular interaction between two atoms in a particular sigma bond. So starting off here, we're going to see that first off, we're going to look at a generic example where we have this particular reagent having an R group, and this is attached to bromide, and this is going to be interacting with metal with a 0 charge on it, and this is going to be done in a solvent which is an ether solvent. So this is actually a diethyl ether. What is noticed now is that there is a change in the oxidation number from 0 to a 2+. So in this case, is to arrive at that, what we see here is that our bromine here has a -1, and on this other side, our R group will have this particular charge right there. So what that happens here is that if we sum the charges when they are actually at separate entities, it's actually going to result in -2, and we don't know what is, but this is now equals to 0 because the overall charge on this particular molecule here is actually equal to 0, and what that results in is that as a positive charge of 2 doing this particular reaction actually loses 2 electrons to establish this particular compound right here. And now this compound is actually known to be a Grignard reagent, and this Grignard reagent, when it's actually in a solution, further the ethers coordinating with this particular, but the overall charge on this right here is still +2 because ethers, they don't have any charge when they are actually standing alone. So that's about it for this particular part here of oxidative addition. And another one we're going to look at, if we have a specific, let's say, reagent which has this attached to a bromide, and this is actually going to react with a Palladium catalyst that we talked about on our previous videos. This is going to be interacting with a phosphenyl or triphenyl, or I would say 4 of them in here. What we notice is that palladium actually has a charge of 0 in here because it's actually having 10 electrons in this particular complex. So our goal now is to be able to coordinate this here with this right there, and we need to target or focus on a specific bond. Now the specific bond that we're going to break now is this particular bond right here, and what that results in is the formation of our product. But now for this to be activated, it needs to actually lose this particular ligand right there, and once it loses it, then it's activated, and then it actually lose another one in there again in order for we to be able to actually generate this particular product. This is actually the essence of our oxidative addition, and what we notice now is that in here we see that there is an increase in the oxidation state from 0 in here to 2. Reason why is because bromide on its own actually exists as negative, and on this side here, which is this other ligand, it actually exists as a negative charge right there. So what the result now is that, okay, the sum of the charges here is actually equals to -2, and then if you actually taking it to the equal sign, we actually get our palladium here to be now +2. So that means palladium actually loses 2 electrons in order for it to establish this new complex right there. So that's about it for this particular part, where we actually have the oxidation occurring in a, I would say, polarized bond or electrophilic species, which is what we have right here. And this actually contains at least one electronegative atom, which is what we have right there. So this actually shows that we are able to not only do this particular reaction, but also perform a form of reaction called hydrogenation, and this is actually done through this particular reaction, where we have this particular element is actually a transition metal, and this interacts with 3 of them, actually coordinating with this particular metal, which is a transition metal. And on one side we actually have chloride actually interacting with this particular metal. So what we notice now is that the charge on this particular metal is actually +1. Reason is because the overall charge on each of these particular, I would say, ligands shows that chloride has a -1 charge, and then if you put it into the equation, which is -1 equals to 0, and this is actually a sum with this particular metal, we actually notice that this metal loses 1 electron, and this causes its overall charge here to become 1. Now what we notice is that there is a hydrogenation process that actually results in the introduction of both hydrogens on this particular, I would say, metal. So what that results in is that we have actually the loss of one of this particular ligand. However, we actually have a more condensed orbitals in there that we allow or accommodate for one particular bonding to occur on this particular metal, and this actually results in this metal actually having hydrogen attached on sides right there, as to we have our chlorine present. What we notice now is that the overall charge here is actually now going from 1 to actually 3 on this particular metal, because this metal now is actually losing 3 electrons, 1 coming in here, -1 from the hydrogen, -1 coming from this hydrogen, -1 charge coming from chloride, and that actually sums up to become -3. Moving out to the other side of the equation, we have +3 going to the metal, and what we see now is that the metal loses 3 electrons in the process right there for this hydrogenation to actually take place. So that's about it for this particular second part, and the third one here is actually looking at a situation where we have better mechanisms or possible transition state that includes the following. Now, if we have this particular metal, which is palladium, of course, which has overall charge of 0 and is attached to 2 of the same, I would say, ligands right here, what we'll actually notice now is that this actually is going to be reacting with, I would say, a phenyl iodide, and what we get in this particular reaction is that, hey, there is something quite interesting happening, which is a transition state where we actually have palladium coordinating with not only iodine, but iodine coordinating with one particular atom on this particular ring right there. So what that result now is that there is this triangle of bond breaking and bond forming between palladium, the phenyl group, and that of iodine, and this is actually going to be done in order for we to establish the formation of bonds in this particular reaction. So this is actually the transition state that is established, and this will actually result in the formation of our product, which is actually shown right here. That's about it for this. And what we notice now in this particular starting material here is that the overall complex has 14 electrons, 14 in the sense that palladium has 10, and 2 electrons coming from the both ligands there gives us the sum of the electrons on this particular metal complex to be 14 electrons. Now this is going to change, where in here we're actually having 2 electrons lost from palladium, which actually results in 10 electrons going to 8 electrons, and we have 4 bonds in there. So 4 bonds means that we have 4 times 2, which is 8, so 8 plus 8 gives us 16. Now 16 electrons in this particular metal complex still makes this particular complex to be highly reactive. So that being said, we actually have to come into something quite interesting with respect to this reagent, where if we compare it to other reagents of the same groups, we actually see that the increase in the bond strength actually results in we not actually favoring the reaction to go in the forward reaction, going from iodine down to bromine to chlorine and finally to fluorine right there. So that being said, what we can infer is that the oxidative addition is faster with weak carbon hydrogen bonds. Here greater than this is a little bit greater than that, and this here is much more greater than that right there. So that is about it for this particular video. All the same, stay smart, believe in yourselves,